You know, our planet is never still, and a huge part of that constant motion is driven by a hidden force we rarely see, the ocean's engine. We're talking about a powerful global network of currents that shapes our climate, fuels entire ecosystems, and, yeah, directly impacts all of our lives. So let's get this engine started. First, let's just wrap our heads around the scale here. Over 71% of our planet is covered by ocean. And this vast expanse of water, it's not just sitting there. It's Earth's #1 energy storage and transport system, constantly soaking up heat from the sun and moving it all around the globe. And that really is the key. This water is in constant dynamic motion. So what exactly is it that drives this massive global circulation? What are the physical forces at work that keep it all moving? Well, that's exactly what we're here to break down. Here's our roadmap. We'll start by looking at the ocean as Earth's circulatory system. Then we'll dig into the forces that shape its flow. We'll trace the incredible path of the Great Ocean Conveyor, see how currents connect directly to our climate and weather, and finally, explore the ocean's vital role and the serious risks it faces today. Honestly, the best way to think about ocean currents is to picture them as the planet's circulatory system. It's a great analogy. Just like blood moves oxygen and nutrients through our bodies, these currents transport heat, gases, and vital nutrients all across the globe, helping to maintain Earth's delicate balance. Okay, so what are the specific forces that are actually powering this planetary engine? Because this immense movement isn't random at all. It's the result of several really powerful interacting factors all working together on a massive global scale. It really boils down to four main drivers. First, you've got surface winds, like the trade winds, literally pushing the water along. Then there's water density, which changes based on temperature and salinity. That is, how salty the water is. This makes water rise and sink. Then you add in the Earth's rotation, which gives us the Coriolis effect. And finally, the continents themselves, which act like giant walls that direct the flow of water. So these forces create two really distinct types of currents. Near the top, you have the surface currents. Think of them as the sprinters of the ocean, whipped up by the wind in the upper few hundred meters. But way down below are the deep currents, the marathon runners, creeping slowly along the ocean floor, driven by tiny changes in density. Both of them are absolutely vital to the whole global system. Now, let's zoom in on a concept that's super important but can be a little tricky: the Coriolis effect. It's essential for understanding any large-scale motion on our planet. The interesting thing is, it isn't a true force you can feel. It's an apparent one, an effect we observe simply because we live on a rotating sphere. So, how does it work? Okay, imagine trying to draw a straight line from the center of a spinning record out to its edge. Because the record is moving underneath your pen, the line you draw is going to look like it's curving, right? That's basically the Coriolis effect. As our Earth spins, any moving water gets deflected from a straight path. It curves to the right in the northern hemisphere and to the left in the southern hemisphere. And the big result of all this constant deflection, combined with the wind and the boundaries of the continents, is the formation of these huge, rotating ocean currents. These massive circular systems are what we call gyres. All right, now let's put it all together. When you combine the wind, those density changes, and the Coriolis effect, you get something truly magnificent: the Great Ocean Conveyor Belt. It's the single interconnected global circulation system that links all of the world's oceans together. The scientific term for this deep ocean system is thermohaline circulation, and the name itself tells you everything you need to know. Thermo refers to heat or temperature, and haline refers to salt content or salinity. These two factors together determine the density of seawater, and it's that density that drives the entire conveyor. So the cycle kicks off in the freezing polar regions. As sea ice forms, the water left behind gets much colder and much saltier, which makes it incredibly dense. This super dense water sinks all the way to the ocean floor, starting a deep current that travels across the globe. Eventually, thousands of miles away, that water warms up, rises to the surface in a process called upwelling, and then flows back to the poles as a surface current to start the whole long journey over again. And that journey takes an unbelievable amount of time. A single drop of water can take about 1,000 years to complete just one full circuit of this global conveyor. It really drives home just how slow, methodical, and powerful this planetary process is. Okay, so we've got the mechanics down. Now let's talk about the impact. How does this constant, massive movement of water actually affect our global climate and even our day-to-day weather? Well, the effects are profound. The Gulf Stream is a perfect example. This is a powerful, warm surface current that acts like a massive heat pump, carrying tropical warmth from the Gulf of Mexico all the way across the Atlantic. And the direct results? Western Europe has much, much milder winters than places in Canada that are at the exact same latitude. It's a textbook case of global heat redistribution. Upwelling is another incredibly critical process. This is when those deep, cold currents finally rise back to the surface, and they bring with them a huge supply of nutrients from the ocean floor. These nutrients basically act like fertilizer for the ocean, fueling explosive growth of phytoplankton, which forms the very base of the marine food web and supports some of the world's biggest fisheries. But sometimes these current patterns can shift, and when they do, you see dramatic results across the globe. The El Niño Southern Oscillation in the Pacific is a prime example. During an El Niño, the trade winds weaken, and that allows a huge pool of warm water to spread east across the Pacific. The result? You can get devastating floods in South America and severe drought in Australia. La Niña is pretty much the opposite, with stronger trade winds, cooler water, and a totally different set of impacts, like heavy rains in Asia. This brings us to the ocean's broader role in the Earth's system and the really significant pressures it's facing right now. Its job goes way beyond just moving water and heat around. This is so important. The ocean is our planet's largest active carbon sink. It absorbs a huge portion of the carbon dioxide that we release into the atmosphere. That CO2 then gets transported by currents down into the deep ocean, where it can be stored for centuries. It's an absolutely essential role in regulating our planet's climate. But there is a serious consequence to all this absorption. As the ocean takes up more and more CO2, its fundamental chemistry actually changes, causing its pH to drop. This process is called ocean acidification, and it's a direct threat to any marine life that builds shells or skeletons. We're talking corals, oysters, and countless other species at the base of the food web. The energy stored in the ocean doesn't just regulate climate. It can also be unleashed in incredibly destructive ways. The case of Typhoon Haiyan back in 2013 is a powerful and tragic example of this reality. Typhoon Haiyan grew over a part of the Pacific Ocean where the surface waters were unusually warm. This extra heat acted like high-octane fuel for the storm, supercharging it into one of the most powerful cyclones ever recorded. The incredible energy it released created a catastrophic storm surge, showing the direct and devastating link between ocean heat and the raw power of our weather. And all this brings us to the most critical question. This entire finely tuned system we've just explored, from the gyres to the Great Conveyor Belt, it's all calibrated to very specific temperature and salinity conditions. So as our climate continues to change and our oceans continue to warm, the stability of this vital circulatory system is one of the most urgent scientific questions of our time. Understanding this ocean engine isn't just an academic exercise. It's fundamental to understanding our planet's future.